for General Chemistry 2 students, I am going to go ahead and walk you guys through this whole process. So let me break it down for you. Now, whenever you all talk about rate laws and expressions, here's what you've got to know. That is dealing with the reactants, okay? Let me zoom in a little so you all can see this. It's dealing with the reactants. So if you noticed here, you've got coefficients, right? Oops, there we go. You've got your coefficients. Well, the thing is, the rates are going to be written out with your coefficients on the bottom, okay, on the denominator, okay? So whenever you're doing your problems like this, you're going to write out, basically, the reactants are going to be negative. So you're going to say 1 over whatever that coefficient is, which in this case is 2, and then you're going to put the change of the hydrogen concentration over delta T, which is the rate in time. That's equal to, again, another negative sign because we're talking about the reactant side. Now, remind you, there is a 1, imaginary 1 there, but we don't have to put a 1 there because it's understood. So what we're going to end up with here is just delta, a negative delta change of oxygen over delta T. And then for the product side, though, you're going to actually have a positive side. So that's going to be 1 over 2 times the change in water over the change in the time, okay? So what you have here is first looking at your chemical reaction, using the coefficients to write the rate. Now, you actually have to use this step here in working with the balanced equation, and there is a difference between the rate expression, which deals with writing the balanced equation using the coefficients. Now, when you do the rate law, this is using concentrations raised to those powers. And we're going to actually go through those processes momentarily, okay? Now, when you do examples like this, again, if we look at this next example here, you've got nitrogen plus hydrogen giving you NH3, which is ammonia. You're going to, again, put the coefficient on the bottom. That's what you see here. On the top, you're going to put in brackets the concentration of nitrogen over the change in time, the concentration in time. Same thing for hydrogen. You're going to put the hydrogen over the change in time, and the same thing for ammonia, okay? Same thing right here. Now, when you do that, that's going to allow you to give the rate expression, okay? So again, all these examples here are called the rate expression. When you're dealing with the reactant side, the rate side is going to be negative. So for potassium chlorate that decomposes into potassium chloride and oxygen, both the one side over here for your reactant is negative, but when you look at the product side on the right-hand side, those are positives, okay? Those are positives. Now, what you're going to do, all right, you're going to use this information here for the next step, all right, for the next step. So in chemistry, when we're dealing with kinetics, okay, kinetics, you're dealing with concentrations and you're having to determine, how drug metabolisms work, how alcohol metabolisms work, how enzyme reactions work within your body, all right? Now, as we move forward though, okay, I'm just going to give you all this facts here one more time to reiterate this, and that is rate law deals with only the reactants now, okay? So when we're looking at the rate law, we've got a balanced equation. And again, this is a generic version of it. We're going to take that K, which is the constant. And in brackets, it's the concentration raised to the power of X. And in another bracket, B raised to the power of Y. Notice we're only dealing with the reactants. We do not look at the product side, okay? We do not look at the product side. So now, what we're going to do, we're going to go ahead and move on and look now at how to calculate this information. What I want you guys to understand is that you have to know what we just did in the first step was exactly that, okay? It was the first step. Now, suppose you are given data. You're going to learn how to move from just writing expressions to actually solving for the order and rate constant using experimental data. So that's what we're doing here now. So for your practice problem, you're going to do a rate law determination, okay? And in each of these problems, I'm going to give you experimental data, and you're going to have to find out the rate law, the K constant, and the order, all right? So here is your first part of information right here. Okay, and matter of fact, I'm going to actually write this down on my other part of the board so that you guys can see how all of this works. Okay, so I'm going to actually do some data over here on the other side, and I'm going to break down what you see. Okay, I'm going to break down what you see. First off, let's take a look at the decomposition of hydrogen peroxide, right? What you noticed here, if we look at just these first two data points right here, what you notice is that your concentration, see this? It goes from 0.10 to 0.20. It doubled. See that? Let me zoom in a little so you all can see that right there. It doubled. And because it doubled from 0.10 to 0.20, what did you notice here about your rate? It also doubled. Okay? It also doubled. Now, because both of those have doubled, we now need to do what? We need to write the order with respect to hydrogen peroxide. So over here on my board, all right, I'm going to write the data out so that you guys can see what we're talking about, okay? So right here, we've got H2O2. See that? If you notice here, the concentration doubled right here from 0.10 to 0.20. All right. So it doubled. Now, the rate also doubled right here. It also doubled. So because both of those doubled, I'm going to show you all how to write the rate law. Okay. So you want to do several different types of observations. Here we have to say that the rate equals your K times, and we're only looking at the reactant side right here. So what you got right here is the rate law, okay? Because they both doubled, because your concentration doubled and your rate doubled, this would be first order, okay? This would be first order. So back to our question right here. It says, what is the order with respect to H2O2? Is first order because they both doubled. And because they both doubled, that gives us the first order. Our rate law is only respective to the reactant. So in brackets, I put H2O2. Now to find the K, because over here it says calculate K, here's how we're going to do this. K equals, and I'm going to have to break this formula down because I want to make sure that you guys can see exactly how this works. Thank you for the roses. Because we're looking for K, we're going to divide both sides by H2O2, okay? So right there, we're going to cancel those two sides out. And so our K that's left over here is equal to the rate divided by H2O2. See that? Okay. Now, why am I showing this to you? Because it asks us to find the rate, or I'm sorry, the K. And because of that, we're going to put up here on the very top the rate here from our data. Okay. Let me go back to our data so you all can see that. Okay. See that right there? That 0.012, we're going to put that on the very top, and on the very bottom, 0.10. So we're going to divide these two numbers right here. Okay, you see that? We're going to divide both of those numbers right there. Okay? So I'm going to put 0.012 and put your units there. Okay? Units are important. You're going to put your units there. Molarity per second divided by 0.10 molarity. Now, when we divide those two numbers, again, we're going to cancel out our molarities because we don't need that anymore. And our K here is going to be equal to, let's go ahead and divide those numbers, 0.012 divided by 0.10. And we get 0.12 per seconds. That's what that seconds with the -1 means, per seconds. All right? Now, y'all know we can't just do one problem, right? We got to do multiple examples to make sure that this sinks in to your mind, all right? So